unmuted.
Okay, I hope everyone can hear me okay. And if you can hear me, if you would raise your hand in the GoToMeeting software so we can make sure everybody is on board. Okay, good. Looks like we've got about 40 people here. Okay, I hope everybody can hear me okay. Again, my name is Jody James, and I'm the warning coordination meteorologist here at the National Weather Service in Lubbock. We sent out the registration screen earlier, talked about a Telcon number. We're not using that, and you should have received an email earlier today about using your computer audio. So just use your computer and speakers, and you should be able to hear the audio okay. Just a few housekeeping notes before we get started. The webinar will cover Advanced Spotter Training. Now, a little caveat about that. We're not going to cover any of the basics. In fact, this is just a few sort of special advanced topics. And it says there it'll be our final Skywarn webinar this year. We really didn't do a basic webinar. We'll probably do that again next year. And again, this course is really designed for the National Weather Service Lubbock area. That won't be as much of an issue with the topics that we'll be covering tonight. This webinar should be about an hour in length, and we're not planning on taking a break. And if you're not a spotter but you would like to become one, we like to recommend that you check with your local emergency management director in your area and also your local National Weather Service office for local training requirements. Every NWS office does things a little bit differently, and some groups may not recognize this particular training. We are recording the webinar, so if you have some friends who didn't get to see that and missed it, we will post the video if everything works out okay. We will post that on the NWS Lubbock Skywarn page, so look for that on that page in the next few days. And we will send the slides out and provide a certificate for those who complete the training. You have to be here for the whole training, though, and we can monitor that in the software, and we'll send you out a certificate that you can fill out for your purposes. We will try to get to most of the questions in the webinar, but if not, you can send those to us via email later if you had some specific questions that perhaps weren't answered. And we're going to monitor the LubSpot hashtag on Twitter tonight. So if you want to ask a question that way or tweet about this particular training, we'll watch that. So thanks for joining us tonight. We appreciate you being here, and we actually only have 2 forecasters here this evening. And by the way, there is the spotter training certificate of participation. It will say Advanced Spotter Training on that. This is the one from last year. Again, my name is Jody James. I'm from the NWS Lubbock office. I'm here with Jonathan Guzman, who's a forecaster. Matt Zebel, the forecaster chaser extraordinaire, will not be joining us tonight because he's in the next room monitoring severe weather. We have a line of storms that has developed just to the west of Lubbock, marginally severe storms, so he will not be here tonight. So we're going to get into our advanced spotter training. I want to show you a few of the training objectives that we'll be looking at tonight. The first one, and this is one that Mr. Zebel put together, how the LCL and LFC influence a supercell's appearance. Those are, if you've ever studied a thermodynamic diagram, those are critical points in the atmosphere, levels above the ground, if you will, that determine the stability characteristics and when an air parcel, i.e. rising air in a thunderstorm, will take off or when it's a more stable layer and it has to be forced to rise. So we're going to look at that for each one of these topics will be somewhere in the range of about 15 minutes, 15 or 20. The second topic is Mr. Guzman is going to talk about bow echoes and various features associated with those. And the last topic is I'm going to summarize some information, the current state of the science, if you will. We're not going to go too much in depth, but we're going to look at what we know and what we don't know about tornado formation in some of the research that's out there and what the future for tornado research is. So again, right now I'll turn it over to my esteemed colleague, Mr. Jonathan Guzman, who hails from Cincinnati, Ohio, long way from home.
Alrighty, our first topic here we're going to talk about this evening, as Jody already alluded to, was looking at the appearance from being out in the field and storm spotting, how different the level of free convection, or the LFC, level of free convection, and the lifting condensation level, the LCL, differ here, and we'll go over exactly what each of those mean for any of you that may not know. So the first one here, the lifting condensation level, something we look at again on the thermodynamic diagrams. That is where your air parcel basically is forced to and begins to condense. So it's essentially your cloud base where your temperature and dew point temperature come together. And that's, again, where you start to see clouds form right there at that height. And then the level of free convection is actually where that saturated parcel of air, so again temperature equal to the dew point temperature, can actually begin to rise on its own and freely due to an unstable atmosphere. So looking at these two in retrospect out in the field and being able to decipher which one it is you are seeing, and in some instances they can actually be at the same height level. So here looking at what we call a skew-T diagram, again looking at thermodynamic properties, essentially temperature and moisture throughout the atmosphere. That red line there on the right is the atmospheric temperature as you go from the surface at the bottom of the figure up aloft, in this case 20 to 30,000 feet into the sky. So from bottom to top of your screen there, we're actually rising in the atmosphere. And then the line there on the left in the green, that's your dew point temperature. So keeping in reference what we're looking at there. And then here if we trace out an actual, what we call an air parcel, so it's a theoretical sampling of air, and this is in the white line here. When we raise those from the surface up and until they become saturated, they actually cool off a lot faster. So that's kind of why you see that steeper curve there, and then kind of flattens and is not as steep, doesn't decrease as much as you work up in the atmosphere aloft there, and that's where you actually see saturation occur, where that inflection point is in that white line. And to give you a little reference here too, we talked about height from going up from bottom to top of the screen. But as you work from left to right on this diagram, your temperature increases. And then conversely, when you go right to left, the temperature is decreasing. So kind of give you, again, a general reference on these. But where we start to look for those features we're talking about here in the field, just to give you background, that area shaded in the light blue there would be a stable layer. So where we wouldn't expect any air parcel to be able to rise quite on its own. Sometimes we'll call that a cap in the atmosphere. So you get that warming nose of temperatures there where your red line starts to go back off to the right as it goes up. And then above that there in the red, so where that parcel of air, again, that we're theoretically lifting in the atmosphere, where that's actually warmer than your environmental temperature, that air parcel can rise freely throughout the atmosphere there. So that's what we would term an unstable layer. So that air is basically going to just keep going in the direction that it's originally forced into, either upward or downward. And in cases here, we're talking with thunderstorms and convection, it's going to be going upward. So your lifted condensation level there, again, LCL, where that cloud base is, that's right at that inflection point where your air parcel becomes saturated as you start to lift it. Because remember, as we lift air, it rises, cools, and condenses. And then there, again, where that air parcel becomes warmer than what your environmental temperature is, again, that can ascend freely and rise on its own, and that's where that level of free convection is. So looking at this in terms of severe weather, this diagram certainly is very conducive of a supercell being able to generate and survive with time. And the more area you see there between that white line and the red line, the air parcel and the environmental temperature, the more area you can shade in there, the more instability we have in the atmosphere for storms to be able to generate and sustain themselves. So again, supercells, as we've gone over, if you've been to basic spotter training before, the difference with those as opposed to other types of thunderstorms are they have a rotating updraft, or what we term a larger scale rotation in a mesocyclone with them. So due to having that rotation about them, they can actually sustain themselves on their own and actually serve as their own source of rising motion and a lifting mechanism, say not having to have a distinct boundary at the surface in terms of a front or a dry line boundary out in the plains to lift that along. So even if you are stable in the low levels there too, again, that rotation about the your supercell with that mesocyclone can actually help that stable air below to rise to your level of free convection. And that's due to a lot of small scale differences in the atmosphere and what we call a pressure gradient force. So you hear high and low pressure, basically large scale differences between those two in a relatively confined area. And then just another tidbit, that pressure gradient too, here we're talking more vertical in terms of thunderstorm motion, but if you ever go about and read anything or hear pressure gradient, say between West Texas and say New Mexico or nearby areas, that's actually what drives the wind when we talk in the horizontal pressure gradient. So once that mesocyclone can't lift that stable layer of air anymore, then that's when the supercell is going to dissipate, or if it can't do it at all, you'll never actually get a supercell to be able to develop and take off. So we'll go through here several different photos. I know Matt took some of these. He may have taken all of them, but from out in his days chasing, and look at the difference here between that level of free convection and the lifting condensation level. So here you see a classic supercell off in the distance with that smooth laminar appearance, indicative of your mesocyclone there. But you can tell kind of just by how smooth and real laminar that is. There's no real crisp edges or any rugged motion or nature about that. So you know you've got a layer of stable air there, and it's actually being forced to rise by that rotating updraft in your mesocyclone. But if we get up aloft there, you see a little more rugged appearance about your cloud elements there, a little better texture to it, not near as smooth or circular about it. So those parcels are going to be more unstable aloft and actually be a little more buoyant. So again, forced in one direction, they continue to move in that direction until stopped by some outside force there. So those are rising a lot faster than those stable parcels down below. And then again, you got to keep in mind that this entire mesocyclone and feature here is rotating, likely in a counterclockwise type motion. So looking the difference between the two, your lifting condensation level is again where your cloud bases are down below, and then that level of free convection is going to essentially be where the cutoff is between your stable layer below, where those parcels are being forced to rise, and then up aloft to where you get that more rugged texture type appearance, and you've actually got better instability above where we looked at on that skew T diagram earlier, where your air parcel you're rising is actually warmer than your environment around it. And again, you can see imagine kind of the rising motion being forced there between the LCL and the LFC, and then a lot more so and with greater momentum above the level of free convection. So here, looking back to the same diagram we looked at earlier and kind of showing you what we just looked at. Again, that red area there being your air parcel is warmer than your environment, so you're unstable. So those are going to, again, be more textured and more cumulus type cloud there. So kind of, again, those puffy cotton ball type looking clouds versus down low in the stable layer where it's a smoother looking in appearance and not near as rugged. Another example here, again, where your cloud base is. So that's really the easy one in most cases, your LCL. And then you see that kind of the flying saucer type flare out. Okay, I want to thank everybody for letting us know the audio seemed to cut out there, so I'll go back just a couple slides here and okay, fortunately most of these examples were pretty similar in nature, so I'll just kind of hit the highlights here on the few and then show you that contrasting example. But here on this several different supercells, more of a classic type here with your precipitation cascade off to the right. You see the level of free convection well above your lifting condensation level. So again, the contrast being the LFC being above that smooth laminar area and having the more cumulus tight cloud appearance above it. And here a little better zoomed in image detail, again the LCL being at cloud base height, and then here you almost have two smooth laminar bases about this updraft base here. So again, above the LFC you start to see that more cumuliform, rugged type look to your cloud tags up there. And then a low precipitation type supercell here. You won't really see a whole lot of precipitation falling out of it, and not a whole lot of breadth to the whole updraft base here. But LCL, again, where you see condensation beginning to take shape, and then the level of free convection above that, you start to see the more rugged, again, cumuliform type cloud above that. And this is the example where we wanted to show a little bit different. You don't really see any smooth or laminar appearance here as we did in the past several examples. It's all kind of cumuliform and textured. But if we did see this in real time in a video type setting, you would notice it is rotating counterclockwise. And here we've actually got that LCL and LFC at the same height. So again, your LCL, pretty self-explanatory, your cloud base, and then above the LFC is where you start to see your more cumuliform and textured clouds. So you've got that right above where your LCL is. So it doesn't always have to be above where your LCL is at, but in this case, both at the same level. And then here we'll change up that skew-T thermodynamic diagram a bit and show you how it looks when they're more equalized. So here you see the red temperature line, so cooling off and decreasing with height as we go up on the figure and to the left. And you notice that it just continues to decrease as opposed to our last example we looked at of this diagram where it actually went back and increased to the right with height at a certain point. That created that stable layer and caused our level of free convection to be above where the lifting condensation level is. So here, since it decreases the entire time throughout the atmosphere, that's actually what causes that unstable layer here, basically from the surface all the way up to the top of our thunderstorm cloud. So this is what we mean here when we talk about surface-based thunderstorms, being able to realize the temperature and moisture all the way down to the ground level. And then again, another example here where we're looking at the same height, and a little tougher to contrast exactly that smooth versus textured cloud element. But again, easier in real time or out in the field spotting this. But just to show again, they can be at the same height. And then two, I want to go back here and touch, just to make sure it's clear, your LCL and LFC, if they're not at the same height, the LCL is always going to be below the LFC, because we obviously can't have cloud element occurring below where our lifting condensation level is, where that initial stage of temperature reaching dew point and condensation's at. So here looking, we talked about extensively in basic spotter training. So when you have that laminar cloud, not necessarily always meaning that we have a mesocyclone and implicit rotation with that. So here moving in this image kind of from the back and right kind of toward you as you're looking at it, and off to the left here a shelf cloud. So again, the LCL being the base of that, and then the LFC above which we see again the more cumulus type nature to the clouds. So with the shelf cloud, again, you've got the warm moist air kind of rising up and over that cloud edge there, and then the cold moist air and denser air behind that pushing it outward, and that's where you get that protrusion kind of on the bottom of the shelf cloud feature there. And again, our greater rising motion as you get above your level of free convection there and start to get the cumulus type clouds to build. So let you guys ponder this for just a second out there. What do you think of this one? And try to use all your clues here. But does it look like we have some kind of triple-decker mesocyclone going on? Or give you a minute to think. And if you notice here, we're in, this is superimposed across a couple of mountain peaks, or maybe a mountain range if we'd expand this picture out. But what we've got here is essentially several different, sometimes we call lenticular clouds. So it's air being forced to rise up over those mountain edges and peaks, and then due to that air motion actually rising up over the mountain and then begins to sink as it comes down the leeward side, you actually get that cloud to kind of anchor itself right there where you've got that sustained area of rising motion, just being on the topography there of the mountain slopes. So you'd likely see this persist with time, and don't think I've ever seen one in real time where you get that stacking there, but certainly can happen, again, more where you've got topographic influence. So a few tidbits to kind of remember here, as we've touched on with the LFC and LCL, and a few we haven't hit on as much. But when talking about stability, of course, the warmer and more moist we are, the more instability we have. So as you get towards sunset and into the overnight hours, you start to lose that instability, and you actually become, your atmosphere becomes more stable. So that can cause the LCL heights to actually lower as our temperatures cool, so you'd reach condensation a little quicker as you work up from the surface. But as it says there, your LFC can remain the same, or actually even start to rise as we lose that amount of instability down low. You can actually get what we call elevated thunderstorms to begin taking over from the surface base during the afternoon when we have peak heating going on at the ground. And then the supercell's updraft, as a result of that, could start to look a little more laminar, farther up from the LCL up, again, just in accordance with losing some of your instability there. And then nice photo off in the distance here from June of '99, where we've got a decaying cell as we're losing instability near the surface before sunset there. But you can see there with time, you're going to start to see that smooth laminar edges of your cloud, your updraft base there, begin to kind of deepen, and that cumuliform layer begin to rise as you start to lose your instability throughout the depth of the atmosphere there. And then again, if they are farther apart, likely means that you're more stable, so tornado potential is less as that occurs, which makes sense as you get into out of peak heating and into the cooler time of day diurnally. And then as a result of that, that spin near the surface that's picked up into the thunderstorm updraft, vertical vorticity there, actually begins to become less there below your level of free convection as a result of that. But keeping in mind, again, that we have rotating thunderstorms with mesocyclones being that larger scale rotation, and if those are strong enough, you can certainly still get tornado production. But again, they have to be somewhat stronger than what you see during the day with better instability. And if they're the LCL and LFC are closer to the surface, likely meaning you've got greater instability, so a higher chance of tornadoes, and you've got less lift is needed to get to that level of free convection at that point, and then again also leading to higher amounts of instability there, and likely lower lifting condensation levels, so that cloud, that rotation that begins at the cloud base doesn't have as far to work toward the ground level to get a funnel cloud to extend from that cloud base down to the ground and become a tornado. And then your vertical vorticity again, so that spin is going to be able to be stretched near the ground a little quicker just due to having less distance to have to work with. And then again, the greater instability all kind of works as a positive feedback on one another, being a better requirement to get tornadogenesis. And then a study, as Matt documented here, where you get below about 5,000 feet or so, or a couple of kilometers, LFC heights below that are obviously more favorable for tornadoes. So kind of a hard rule we'd use when assessing the environment early in the day to kind of look at tornado potential early on. All right, so we're going to move into a little different phenomena than we see Okay, moving on to a little, I said, different phenomena than we see out here in the southern Great Plains on a majority of the time. You see these more as you get into the Midwest and often in the Great Lakes and kind of east of the high plains of the U.S. And talk about bow echoes here, and then several different kind of categories that go along with those, ranging from convective complexes to smaller scale circulations that can be embedded in these. So the definition of a bow echo, essentially a mesoscale, so kind of a smaller scale convective system that's got that bow shape when you look at radar reflectivity, and usually has a very tight gradient in reflectivity intensity along its leading edge there. And the ranges of them can vary depending on how many there are and what exactly is forcing them. And your biggest severe weather threat with these is going to be damaging winds. And as opposed to a tornado where you've got the rotational type wind with that and damage, these are in one unified direction, in the direction of storm propagation. So in this example here on the bottom would be off to the left and maybe down to the south to a bit, so off to the east and east-southeast. And for us here on the plains, most common when we get northwest flow aloft and some semblance of westerly flow across much of the country where these do occur is going to be the general rule. But speaking just solely here in West Texas, when we get into, say, June, the June time frame when we get convection to develop in the mountains of New Mexico and the higher terrain, that can actually help to drive these when we get northwest flow aloft there down into the plains of West Texas. And then just comparing here what we'd see between reflectivity there on the left and what we call base velocity, or again where we're seeing moisture and cloud element, the motion of those in the atmosphere. A few various aspects to look at there. On reflectivity, again, you see the bowed out shape and the reflectivity gradient along the leading edge. And then with these, you can also, or do get what's termed a rear inflow notch, or we'll look at in a little bit, a rear inflow jet. So it's essentially strong winds punching into the backside of that system in the direction, again, of storm motion. And then due to that, you can actually get circulations that develop on either side of the bow echo, with normally the more influential and stronger one being on the northern side, and that's due to having that be more of a cyclonic type circulation. So again, counterclockwise motion about that. And then the velocity image there on the right, as you get into the reds and pinks and violet and orange and kind of the orangish yellow there, your velocities are increasing. So you've got 80 to 90 knots, it says here, about 100 miles an hour of wind actually punching into the backside of that bow echo, moving from west to east here across the northern portions of Illinois, or central portions, excuse me, in east of Lincoln, Illinois. And looking here, a study done by Ron Przybylski, who the former Sue. Unfortunately passed away a couple months ago, or just about a month ago, a couple weeks ago, from the St. Louis office. But did a lot of great work with looking at these mesoscale convective systems and bow echoes. And going from left to right in that image down below, you see your convective cell initially, so you've likely got a strong echo at least, or a supercell potentially, and then begins to become distorted there as you move from left to right into a bow echo. And again, you get that rotation, the counter-rotating couplets, cyclonic on the northern edge and anticyclonic on the southern edge there. And then you start to see that echo again protrude out and kind of bow out as you get that hook to really live on at the northern edge there. And here we'll go through those in a little more detail, exactly what's going on in 3 different stages. So kind of looking at a cross-section with what's going on aloft in the atmosphere with your storm, what you'd see on radar reflectivity looking down lower in that image. So again, we start the thunderstorm process with that warm, moist updraft, and then once the downdraft forms, so your more dense, rain-cooled air, starts to spread out again in all directions, and then with those strong winds aloft, that downdraft is going to spread in the direction of your storm propagation and your mean steering flow aloft. So that's what creates your gust front, the leading edge of that rain-cooled, denser air. And then that in turn forces that warm, moist air out ahead that would be feeding into the updraft, forces it upward along the leading edge of that gust front. So you can often but don't have to necessarily get those laminar shelf clouds pushing out ahead of one of these. And remember, immediately underneath and behind those is where you have these severe winds associated with these, and then your heaviest rain and or hail associated with them. Then moving on here, just depending on how strong that upward motion is along the gust front and how much of that turning and increase in speed you have of your winds in the atmosphere, what we term wind shear, vertical wind shear. So just exactly how much of that shear and you have to balance out that what we call cold pull. So again, from your downdraft, the moist, cool, denser air. So the balance between those two, and again, how strong that lift is along the gust front as a result, is going to dictate how much new thunderstorm development and longevity of those you have as this system progresses. And then again, as we alluded to just a little earlier, your rear inflow jet is going to develop on the backside of that, and that's due, again, to very small perturbations in the atmosphere in terms of pressure gradients, kind of wreaking havoc on instability throughout the depths of the atmosphere. So once that develops, it's going to allow, and kind of, again, that positive feedback, allow your cold pool to continue increasing in size as your updraft starts to kind of tilt, in this instance, back to the left or likely off to the west. So kind of rearward with that rear inflow jet protruding the lower portions of that storm outward and to the east in the direction of storm motion. And then again, that feedback continues there as your storm expands and produces more precipitation there with that rear inflow jet and strengthening downdraft. You're going to further strengthen your cold pool and that rear inflow jet. So it just kind of keeps feeding on itself, depending on how much, again, shear you've got to allow that to balance out. So the greater shear you've got and instability to generate stronger storms initially and balance the cold pool, the stronger that the bow echo system can become with time. And then sometimes these can evolve into a larger, more damaging kind of widespread type complex, what we call a derecho. And as it says there, these are basically coined as widespread and long-lived windstorms induced from previous bow echoes and prior convection. So the criteria for these, You get essentially a very large swath of downburst winds extending nearly 250 miles or more. And to be termed a derecho, you have to have a consistent 58 miles an hour, which again is our lower threshold for severe winds. So you have to have basically those kind of more or less piled on top of one another, along with some higher gusts, so say on the order of 75 miles an hour, or it's kind of where we term our significant severe weather threshold in terms of winds. So when you have several of those kind of on top of that consistent lower threshold 58 miles an hour, that's where we can coin that phrase over, say, that 250 mile stretch there. And you can't have a time lapse in more than about 3 hours between successive reports, as that system would move likely off west to east. And then there are two types of these. Serial derecho, they're kind of their own system. So you get very kind of a small scale, low pressure system developed, not what we'd see synoptically in terms of warm and cold fronts, but kind of a micro scale or micro or mesoscale type low pressure system to develop. And then you can get several what we call, if you look at that red line there on the image, line echo wave patterns to actually develop in that. So in that image there, we've actually got 4 bow echo type features propagating along that, just due to that the strength of that system kind of taking on its own life as it moves off with time, as it says there in the mean wind direction off southwest and northeast. And then a progressive derechos, where you basically got one bow echo type feature that's going to move along some sort of frontal boundary, and then the motion of that's going to be dictated by new thunderstorm development along that outflow boundary or stalled out frontal boundary with time, and again in this instance moving off from west to east. And this is one of the better examples of a long-lived, about 600-mile derecho event that started up in northern Illinois and spread all the way to the mid-Atlantic coast. So I was actually in Cincinnati at this time, as Jody said. That's where I hail from, and remember seeing debris fly from this and having no precipitation, so the wind's well out ahead of it, with the gust front on the leading edge, and it was really pretty spectacular to see something as long-lived and strong and violent as this. So as it says, peak winds on the order of 80 to 100 miles an hour were reported, and power outages were just numerous, and several millions. And storm reports there, if any of you look at the Storm Prediction Center local storm reports or your local weather forecast office, these were being pumped out, and just abundant numbers, in the order of 500 to 1,000 with this system. So you can see there it moved at about 60 miles an hour, lasted about 10 hours there. So, and this is again what we would call a progressive derecho. So you kind of got that one large bow echo just progressing along a kind of a west-northwest to east-southeast type boundary as it moved off in time there. And then a smaller scale feature associated with these systems, or bow echoes at times, we call mesovortices. So it's just essentially an area of enhanced shear, usually along that leading edge, so where that tight reflectivity gradient is. And you can get real quick spin-ups, tornadoes to develop with these, and these are really the toughest time to kind of warn for us meteorologists in the Weather Service. The supercell type feature tend to be a lot easier, where you've got one storm and that broad mesocyclone. But these, if you do have a mesocyclone, they're normally very small and pretty transient in nature. And then just keeping in mind, if out spotting in the field, to not give up on the southern storm there. We've talked about the northern storm with bow echoes where you've got that cyclonic rotation likely being stronger and more impactful, but you're going to have your better instability in all likelihood down near where your southern storm is, so where your unimpeded warm, moist, unstable air is flowing into the updraft there. And looking here again, comparing reflectivity and velocity data, and kind of a little tougher to see the exact intensity of the bow here zoomed in, but each 1, 2, and 3 denotions here being co-located. So your radar sights in each image off to the left. So again, the green from basic training is inbound velocity, and the red is outbound. So you've got 3 real small scale but pretty intense mesovortices with that cyclonic rotation about them. And you can see if you're just looking in reflectivity there, you don't see really anything in terms of that hook echo that we see with a classic supercell structure. So these show up pretty self-explanatory in the velocity data, but they're certainly not always this clear-cut by any means. And then a larger scale, one of those mesovortices, what we call a mesoscale convective vortex, can actually kind of morph into one of these a lot of times into the late evening and in the overnight hours, and we'll see these last into the morning hours across the Midwest portions of the country, from the plains sometimes from previous day convection. So these are kind of, again, driven like those serial derechoes, driven on their own, where you get the condensation occurring and what we call latent heat release. So when we have condensation, that requires cooling, so the heat released from that process actually helps to lead to pressure falls and help these to kind of morph into their own little complex. And if you do see these, you'll likely see them rotating in time on radar in a counterclockwise manner right about that point there on the image as they move off, again, normally from west to east. And wrap up here with a famous example. If any of you were in the Lubbock area back in 2001, and I'll let this play one more time here. But you see the classic northwest flow pattern in late May, and then the cold pool and downdraft of that system kick out right as it gets into Lubbock and just west of the city there. And kind of where you see that black arrow pointing, that's just about where Reese Center is, and right there as that bow comes through, actually measured 105-mile-an-hour gust out of that. So you can certainly see damage equal to or more so out of these than with a tornado, and really the net result's the same. It's just which direction your wind and debris would be in. But these certainly can happen out on the Great Plains, but again, normally a little more common as you work farther east. So with that, I'm going to let Jody take over here and finish up with kind of the newest and latest and greatest on tornado formation.
Okay, thanks for staying with us. As Jonathan was speaking there, we had a severe thunderstorm move over the office. We could hear it raining. The warning for Lubbock was for golf ball size hail, and I noticed at my house I received about another inch of rain, half an inch to an inch in a pretty short order of time. So we hope we don't lose the signal. We haven't so far, so hopefully everyone can hear us okay. The audio cuts out because if you don't have a continuous feed of audio, sometimes we lose the signal or it cuts out just a little bit. What I want to do is summarize what we know and don't know about tornado formation, and I'll have some credits at the end. But this is based on a paper that was in Physics Today, and I'll give those credits a little later. To start with, when we look at thunderstorms, we're talking about deep, moist convection. as opposed to shallow cumulus clouds, which would be shallow convection. And as opposed to dry convection, there is convection usually in the atmosphere, and a lot of times that is extends up thousands of feet, but it's not making any clouds, so it is dry. But of course, when we have thunderstorms and tornadoes, we need the deep moist convection to do that. So most of you that have been through spotter training before are probably aware of that. Both of these graphics on the left and right, the U indicates the general updraft region of the thunderstorm. The forward flank and sometimes the rear flank downdraft are where the D's are located. Again, this is kind of a classic supercell. The green is the broad area precipitation, with the darker green being hail. And we don't always see a wall cloud or a tornado develop in the vicinity of the mesocyclone, but if you do, you'll see it in generally that area real close to the updraft and the downdraft interface where we have the T on there. And you can see the corresponding locations there on the picture to your right. But generally, and this is kind of meteorology 101, you need 3 ingredients to make thunderstorms. The first is moisture, the second is lift, and we get the first 2 a lot in the winter time, and we get widespread what we call stratiform precipitation, where the air is lifted. It didn't want to go up, but something is forcing it up, like a cold front, and it doesn't take off like a hot air balloon. The third ingredient, instability, is where we go from warm and humid air down near the surface in the lowest few thousand feet to very cold air aloft, colder than normal sometimes, and also sometimes drier air. Now, when the thunderstorm develops, obviously it's moist, but if we go from warm and humid to cold and dry, that is a very unstable atmosphere, and if we can give the air a little boost near the ground, it will keep rising in a lot of cases. So most of you have seen a graphic like this before in your spotter training handbooks. I won't go over all the details, but this is, as it mentions there, this is inside the belly of the beast. This is the supercell structure, and you can see the updraft and the downdraft. You can see the rotating updraft there and the kind of pink or red arrows there. That is the mesocyclone, the rising updraft, and that is really what defines a supercell. And then we have a lot of the accessory clouds, perhaps a shelf cloud, wall cloud, tail cloud, and others that you've seen before in the basic spotter training. But what I want to talk about now, I won't go into too much depth in fluid dynamics, but we have to talk about vorticity and upward motion and how those areas of spin, be they large or small, in the thunderstorm get moved around, get tilted up, maybe contract due to angular momentum, like a skater pulling their hands in. So in this graphic, we see the arrows indicate where the air is rising, and the longer length arrows indicate where the air is rising faster, where the what we call omega is pretty positive. The air is going up on its own. If an updraft like that develops in areas of wind shear, where the winds, like the arrows on the left there, are going from south maybe to west and north, sometimes they don't turn that much, but they might turn from south to west. You can see if you put a pinwheel in there, you'd get some rotation in that, in the direction you see those yellow arrows. Well, when we take that whole vortex line that may be kind of horizontal to the earth and bend it upward, as you see in the picture there, then we create rotation. We sort of take that spinning tube and tilt it up, like tilting up a jump rope, if you will. So we get cyclonic rotation on one side of the storm and anticyclonic rotation on the other. So kind of keep that picture in mind as we go along here when we talk about supercell tornadoes. The top picture, and we'll go over these in more detail a little bit, but Jonathan talked about that mesocyclone, the rotating updraft that's created by the vertical wind shear. You see the football in there. It's spinning in the way maybe the wind would want to spin it. That's a function called vorticity, a parameter in the atmosphere. So if it's tilted upward, you start realizing that spin on a large scale, several kilometers, maybe sometimes 2 to 3 miles across, and that creates that large mid-level mesocyclone. Sometimes it extends down fairly close to the ground. But don't confuse that with rotation in the wall cloud or tornado, because that is related, but it forms differently. And one of the differences is where that downdraft will help to bend that vorticity, and how successful it is has to do with the stability and whether that downdraft is warm or cool. Now, when I say that, downdrafts are always colder than the updraft air typically, but how much colder? Are they just maybe a few degrees colder, or maybe 10 or 15 degrees colder? That makes a big difference on how much suction you can get and how much you can realize that that vertical motion underneath that. So we'll talk more about that in a little bit. So here's kind of our present understanding of supercell thunderstorms and tornado formation. Of course, all supercells don't produce necessarily strongly rotating low-level mesocyclones, and some never produce tornadoes. So what's going on? Well, in step one, that mid-level mesocyclone that we talked about, that large area of rotation that is the main storm tower sometimes, and you see that spaceship look if it is rotating fast enough. Again, that develops in response to that deep layer shear. So if we get thunderstorms develop on a day where we don't have a lot of turning and increasing of winds with height, then we don't get that rotating updraft. And then that vorticity is tilted into the vertical as the updraft develops. So that's step one. And then step two is buoyancy gradients, and I'll show you a better example of that in just a minute. And what we mean by that is near where the warm air is coming into the storm, just north of that in the forward flank downdraft region, you get warm air on one side, cold air on the other. So imagine that sitting side by side, and imagine which way that would rotate. Now we're talking about down low now, kind of into the storm. Step two on that top picture there. Well, normally cool air sinks and warm air rises. So imagine a vorticity down near the surface coming in from that direction, maybe from the southeast or east. And then that gets tilted up as it comes in and then gets pulled up into the updraft. That can help to generate vorticity and spin down low on the lower part of the storm. And that would be feeding into that beneath that mid-level mesocyclone. So that would be feeding into that area where you have the more large-scale rotation. And of course, as it comes in and it gets lifted upward, it's tilted into the vertical as those parcels descend. And then step three, conservation of angular momentum. That's just a fancy phrase that means like a skater skating on ice, rotating on a large scale, the skater pulls the hands in so the diameter is less, so the spin gets faster. So that's what happens when air is converging toward this axis of rotation and getting stretched upward, sometimes beneath that larger area of spin beneath the mid-level mesocyclone. So I hope you can see that. Basically what we're saying is you get spin coming in the low levels due to that warm-cool gradient, and if it's aligned right and how efficient that spin is coming into the storm based on how the winds are aligned, that can get enhanced and sucked upward by the mid-level mesocyclone. So if you can get that aligned right, your chances of stretching that vorticity down near the ground up into the mesocyclone, and you can increase spin sometimes on the order of 10 or 100-fold with that conservation of angular momentum. In other words, it's sort of pulling into a tighter and tighter spin as it gets stretched upward. So that's sort of our understanding. So what are the caveats here? Well, we'll talk about those in just a second, but you do need just the right gradients there in buoyancy, and sometimes a little boundary can help to enhance that. And then you also need that to be underneath a mid-level mesocyclone and have enough energy and stretching to get up and help that stretching take place. So you see in B and C there, if you've got a relatively warm downdraft, you can get stronger suction beneath that mesocyclone, but if the downdraft's colder, in other words, more stable, you get weaker suction, so you're not as efficient as converting that vorticity coming in from the east in this diagram of being efficient from producing a tornado. So briefly talk about convectively available potential energy. We call that CAPE. That is just the amount of instability. And that's an important topic when we're talking about tornadoes and supercell thunderstorms. Jonathan talked about that a lot, of the blue line being the atmospheric around the thunderstorm, if you will, and the red line being the temperature of a parcel. In other words, a rising parcel of air in that thunderstorm. And the greater that area between the two is the CAPE, and that's one thing we look for as meteorologists. In this example, we have 3,458 joules per kilogram of CAPE. Now we can calculate what that CAPE would be in a situation. It's to refresh your math skills, that's the square root of 2 times the CAPE. So we can calculate in meters per second how that would be. So in this case, that would be about 83 meters per second, which would be about 180 miles per hour. And you say, man, that's a fast updraft in a storm. And you won't always realize that because, well, normally you won't realize that due to precipitation loading and dry area entrainment and things which sort of slow it down from the top level theoretical value. But in the case of a rotating mesocyclone, we can actually enhance those updraft speeds because we're creating low pressure at the top of the updraft due to that rotation, that suction that we talked about in the previous thing. So sometimes we can not only achieve that theoretical level of updraft speed, but we can actually exceed it in the case of incredibly strong supercells. So can we get supercells with 200 mile per hour updrafts? Probably not very likely, but it does happen on some occasions. And when we get that kind of vertical motion, you can see how when we stretch that low level vorticity, it can really contract and turn into violent rotation on a small scale pretty quickly. So really when we get when we talk about tornado genesis, in other words, how do we make a tornado? How does a tornado develop? It's kind of a Goldilocks problem. You don't want it. Number one, you need to intensify near ground rotation, and that can be developed along a boundary. That can be developed along a buoyancy gradient along the forward flank downdraft. So you need to intensify that some way and bring it into the right part of the storm, preferably beneath that mid-level mesocyclone. And then that vorticity needs to accelerate upward and be stretched. Again, this is conservation of angular momentum. Maybe a large scale rotation on the order of half a mile gets stretched down to maybe a few hundred yards, and you get a massive increase of rotational velocities in that. And then the real Goldilocks problem is all of these things, but especially number 3, the temperature of that downdraft is very important. Even though it's a downdraft, how buoyant is it? How resistant is it to upward motion? Remember, we're tilting down some of that vorticity in that part of the storm. So if that downdraft air just does not want to rise no matter what you do, that's not going to be beneficial in trying to produce a tornado. In the case where it's a little bit warmer, maybe just a few degrees warmer than the ambient air feeding into the storm, it can have more success. So that's kind of where we're at. Now, how do we know what we know about supercells and tornadoes? Well, there's several ways we've learned about it. We obviously have the theory in the fluid dynamics, but in the picture on the left here, this is a Vortex 2 mapping out a storm in southeastern Wyoming back on the 5th of June in 2009, showing the winds, the area, the updraft area, and the area of precipitation. So we've observed these storms, usually not as well as we have on these vortex experiments. We can estimate, but these experiments have given us some extra insight into how these storms develop and what's going on, not just in the storm, but around the storm. The other thing that we've learned some things with is computer numerical model simulation. In other words, we make a supercell thunderstorm in a computer. The problem with that is, like with all computer models, it's highly dependent on what you put into it. In this case, one of the problems is it's highly dependent on model physics parameterization. In other words, when you get down to the physics all the way down to the how the raindrops form and where the latent heat is released, and sometimes those are very small scale things, but they really will affect the way the computer model plays out the thunderstorm pretty dramatically. So we have to be careful of the assumptions we make, but we have gotten a lot of insight, and we can see these counter-rotating low and high pressure areas within the storm very well, just as we see out in real life out in the field. So conclude here about future tornado research. One of the things that's going on in NOAA is the Warn on Forecast program. Now this is using computer models and more of an ensemble approach to put in all the parameters of what's going on before thunderstorms develop or even after it develops, the wind, the instability, what's there now, and running that out in time using an ensemble, which means running a bunch of models and taking an average of where it thinks it's going. And we can use that to see what the computer thinks and what are the probabilities that that storm will be in a particular area, and what are the chances that maybe the tornado part of the storm will be tracking in a particular region. Then we can assign probabilities to that in the future, maybe out an hour in advance, and say, 50 miles away, you have a 70% chance of a tornado being within so close to where you're located. So you might hear more about this. There's some other research projects that are similar to this that may have a different name, but the Warn on Forecast. And I guess the idea is eventually, as we meteorologists in the Weather Service would make a warning not based on a storm, but based on a prediction of a storm in a location. So pretty interesting stuff, and we'll see where that goes. So some future tornado research areas. Which supercells produce tornadoes? Why do some produce tornadoes, others do not? What is the real-time tornado intensity? We can look at circulation in the low to mid-levels of the storm and make an assignment and make an educated guess on, is this an F2 tornado, an F3 versus an EF0, for example? But it's difficult. How can we know that in real time? That is a problem. I mentioned the microphysics of supercells, how down to sometimes the molecular level, how's that affecting everything? We still need to know a lot more about that. Surface friction's role. We still have a lot to learn about that. There was a paper recently that came out of Purdue and Indiana that looked at tornadoes based on historical data and storm data information that looked where do tornadoes develop, where do they initiate, and there was some indication that there seemed to be a slightly higher frequency where you change from forest to farmland, or perhaps from a city, urban environment at the edge of a city back to farmland or back to forest. So that surface friction changing, maybe even in fairly subtle ways, or what we thought were subtle ways, may play a role in organizing that vorticity that gets ingested into a thunderstorm. Gap-filling radars like CASA radars, those have gone in the Fort Worth, Dallas area. They're cheaper, and we can put a lot more of those in so we can see details that maybe we couldn't see before. That's kind of something that we'll see more of in the future. And then I mentioned the Warn on Forecast, making a forecast based on a computer prediction. So I've got questions up there. We're about to the end here. I do have a couple of slides at the very end of it, so you do want to hold on. But Jonathan's over in the chat window and has the question window open. So if anybody has any questions, I know I went through that pretty fast, and fluid dynamics is a pretty complicated topic, but if you have any questions on where we're going in the future and anything related to the earlier presentations, we'll be glad to field those now. Again, I wanted to give credit. I pulled some of these graphics and this information out of Physics Today. That was September of last year. That was Paul Markowski and Yvette Richardson. Those are meteorology professors at Penn State University. And they're two that we've seen a lot in the research that has occurred over the last 15 or 20 years, and they specialize in severe storms research. And they, by the way, co-organized the second verification of the origin of rotation in tornadoes experiment we call Vortex, and they've written a textbook. If you want to learn more about this, mesoscale meteorology in the mid-latitudes. So I don't know if they're probably not on the webinar tonight, but I did want to give Dr. Markowski and Richardson credit there. That's an excellent paper, sort of summarizing where we're at. We have learned a lot in the last 20 years, and hopefully we'll keep doing that. I want to thank you for joining us tonight. As I mentioned, I'll be sending out certificates if you were here for all of the presentation. There's my contact information on the screen and my office phone number. Would encourage you, especially if you're in the West Texas area, to go to the NWS Lubbock website. It is at weather.gov/Lubbock. We also have a Facebook and Twitter account and my own personal Twitter there at the bottom. So again, thank you for attending our webinar. Please watch our news, top news headlines. We probably will do at least 2 webinars next year, and we might even have some special topics if you're interested. Send those my way if there's a particular topic. If you're interested in meteorology, or if you're a storm chaser and you would like us to cover something, particular topic, we have a lot of expertise in our office. We'd be glad to do that and maybe focus a 30-minute presentation on a particular topic. So if you attended with more than one person when you registered, more than just the one that registered, please email me with the number of participants. We like to keep track of that. And also, please email me and provide feedback. We'd like to know how you like this webinar and, again, some things you might like to see in the future. So, again, thank you, and we'll be concluding the webinar now, and we will see you next year.